Why build two systems when one already does the job? Two pumps instead of one, backup power supplies, duplicate sensors. At first glance, redundancy can look wasteful, expensive, even inefficient. But in engineering, redundancy is rarely added by accident. It is introduced deliberately, and only when the consequences of failure are too serious to ignore. This is not paranoia or needless over-engineering. It is the result of structured risk analysis and a clear understanding of how real systems fail. In this video, we'll look at real-world examples of redundancy in practice and explore how engineers decide when its benefits justify its cost. At a technical level, redundancy means adding extra components or subsystems that can take over if the primary one fails. The goal is not higher peak performance. The goal is higher reliability. In engineering terms, reliability is the likelihood that a system will keep doing its intended job for a defined period under defined conditions. And redundancy can raise that likelihood dramatically. If one component is very reliable but not perfect, then adding a second path or backup can make the overall system much more dependable, especially when failure would be costly or dangerous. Engineers often analyze this with what are called reliability block diagrams. The idea is simple. In a series system, every required component has to work. So the overall reliability drops as more single points of failure are added. If two components each have a reliability of 0.98, the combined reliability in series is about 0.9604. In other words, either one can bring the system down. But in a parallel arrangement, one component can keep the system running if the other fails. For two identical parallel components with a reliability of 0.98, the chance that both failed during the same mission is much lower. This mathematical framework guides redundancy decisions quantitatively. Consider commercial aviation. Modern aircraft typically use multiple hydraulic systems, independent flight control computers, and redundant electrical power sources. The reasoning is straightforward. The failure of one subsystem must not lead to loss of control of the aircraft. For critical functions, aviation safety targets are extremely demanding, on the order of one catastrophic failure per billion flight hours. Reaching numbers like that with a single component is usually unrealistic. Redundancy, combined with fault detection and isolation, becomes one of the few practical ways to meet those requirements. A historical case underscores this principle. In 1972, Eastern Airlines Flight 401 crashed after the crew became distracted by a faulty landing gear indicator light. The bulb failure itself was minor, but the event showed how a small issue, if not handled properly, can pull attention away from more important system states. Subsequent cockpit design increasingly emphasized redundant warning systems and cross-check logic to prevent single-point distractions from cascading into disasters. The lesson extended beyond aviation. Redundancy must address not only hardware failure, but also human factors. Redundancy also matters far outside safety-critical industries. Data centers rely on backup power supplies, multiple network paths, mirrored storage, and spare servers, because digital services are expected to stay available even when hardware fails. Engineers look at measures such as mean time between failures and mean time to repair to decide how much redundancy is justified. If downtime costs thousands of dollars per minute, then duplicate infrastructure becomes economically rational. The added cost of redundancy is weighed against the expected cost of service interruption. In electrical power systems, redundancy appears in transmission networks. Power grids are often designed to withstand the loss of a single major component without widespread blackout, a concept known as N1 contingency planning. Engineers simulate scenarios where one transmission line or generator fails and ensure the system can reconfigure safely. The probability of simultaneous independent failures may be low, but the consequence of cascading outages justifies investment in redundant pathways. Quantitatively, engineers assess redundancy using fault tree analysis. Suppose a component has a failure rate of 1 in 10,000 hours. If mission duration is 1,000 hours, the probability of failure during the mission is roughly 0.1. Adding an identical independent backup reduces mission failure probability to approximately 0.01, assuming independence. This order of magnitude improvement may justify additional weight or cost in aerospace or medical applications. However, if mission duration is short or consequences minimal, redundancy may be unnecessary. Medical device design illustrates this decision boundary. Implantable pacemakers often include redundant sensing circuits and battery monitoring systems because device failure can be life-threatening. In contrast, a household appliance rarely includes such duplication. The acceptable failure rate differs dramatically because consequences differ. Engineers align redundancy level with severity of outcome rather than theoretical perfection. At the same time, redundancy is not automatically beneficial. Extra components add weight, costs, complexity, and interfaces, and every new interface can become a new failure point. More wiring, more connectors, more software logic, and more control paths can all create new problems. There is also the issue of common cause failure, where multiple supposedly redundant elements fail for the same underlying reason. So engineers have to ask a harder question than just, do we have a backup? They have to ask whether the backup is truly independent. That limitation became painfully clear in the 1986 Challenger disaster. The shuttle had redundant systems in many areas, but the O-ring vulnerability in the solid rocket boosters was shared across the design. Cold temperatures affected the sealing performance of both the primary and backup joints. In other words, the system had duplication, but not protection against the same failure mechanism affecting both at once. The lesson was crucial. Redundancy cannot rescue a design that has a single weakness built into all copies of the system. Duplication helps only when failure paths are genuinely separated. Control systems provide another useful example. Adding redundant sensors can improve measurement reliability, but then the system has to decide what to do when those sensors disagree. One common solution is triple modular redundancy, often used in flight control computers. 3 independent processors compute the same output, and the system compares the results. If one disagrees with the other 2, it can be identified as faulty and isolated. That architecture can improve reliability substantially, but it also adds computational overhead, extra software, and more design complexity. Engineers have to make sure the added logic does not create new delays, bugs, or unexpected interactions. Boundary conditions shape these decisions as well. Budget limits how many backups a project can afford. Physical space limits how much duplication can fit into compact hardware. Maintenance matters too, because redundant parts still need inspection, testing, and replacement. In some cases, it may be better to invest in making one component more robust rather than adding a second weaker one. So engineers compare 2 different paths: improving the reliability of the primary system or adding redundancy around it. The right answer depends on the full life cycle of the system, not just the initial design stage. If you compare different industries, a common pattern emerges. In civil engineering, bridges include multiple load paths so that failure of one element does not lead to collapse. In telecommunications, redundant fiber routes ensure connectivity despite cable cuts. In manufacturing, parallel production lines maintain output during equipment maintenance. Across domains, redundancy is justified when downtime cost, safety impact, or reputational risk exceeds the added system cost. Ultimately, engineers decide to add redundancy by analyzing probability and consequence together. High consequence combined with non-negligible failure. Probability motivates duplication. Low consequence or extremely reliable components may not. The decision is rarely emotional. It is grounded in quantitative risk assessment, economic modeling, and understanding of failure mechanisms. Redundancy is therefore not excess. It is structured insurance embedded within design. When applied thoughtfully, it transforms fragile systems into resilient ones. When applied blindly, it can add complexity without improving safety. The engineering challenge lies in distinguishing between these outcomes. If you value precise, research-driven explanations of how engineering systems are structured to manage risk, consider subscribing to Engineering Manual for deeper technical analysis.